Hi, welcome back to Missing Chemistry. This is electron configuration of osmium OS lesson. Okay, osmium is element number 76. So I'm going to write 76 down right here for our atomic number. And its atomic mass number is 190. Well, since the atomic number is 76, that represents the number of protons in the nucleus, so 76. And since osmium, like all other elements, unless otherwise stated, are electrically neutral, we would have to have 76 electrons. Now, what about the neutrons? Well, basically, again, do AMU minus the number of protons gives you the number of neutrons, right? So here we go, 190 minus 76 would give me 114 neutrons. So I can put 114 right here. Pretty darn cool, I'd say. Oh, I know, I should use the term snarly, because snarly is a new cool. Alright, now clean that up a bit, and let's go ahead and look at this. S can hold 2 electrons, the P can hold 6 electrons, the D suborbits can hold 10 electrons, and F suborbits can hold 14 electrons. We use the off-ball principle, which says fill the lower shells first, and then you go to the upper shells. And we can use the diagonal rule. These diagonal rules are these orange arrows, and you go through these progression until you run out of electrons. How many electrons is that going to be? 76 to be exact. Alright, so let's go ahead and do this. Alright, here we go. So we got 1s2, slide down the slide, here we go, 2s2, 2p6, 3s2, see how easy this is? 3p6, yeah, we max out each suborbit until we run out of electrons. 4s2, amazing. 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, and last but not least, 5d6. Okay. So the electron configuration is done. Now let's look at the orbital notation. Orbital notation talks about Hund's rule. We have to put an up arrow and then you put a down arrow in that suborbit. And the up arrow represents, like this one here, is a clockwise rotation of the electron. The down arrow will represent a counterclockwise rotation of the electron. So let's keep on going here. And then, like I said in my other videos, 2px, 2py, 2pz, here's a classic Hund's. 1, 2, 3, then we go down. 4, 5, 6. That's Hund's rule at its finest. Okay. Again, just keep on doing it until we run out of electrons. Pretty easy. So much fun, I gotta tell you. Watching the arrows go up and down. Alright, here we go. Just humming along. Everything's looking pretty good. This one's got a 7, of course. Also the hardest one to try to remember. Okay, and now we have 6 here. Go up, 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 and then go down. Alright, now the noble gas notation is a means of like taking all this stuff and kind of like making it simple, right? So I'm going to write Xe because that's the nearest noble gas, and then Xe's electron configuration is this guy's right here, right? So that takes care of all that. So then I'm just going to put in numeric order here. Some people like to do it the way you see it right there, but you know what? Numeric order is the best way to do it, in my opinion. And it's the more correct way. I've researched it. So that's what they say, who they are. Sometimes you don't know who they are, but anyway, Pauli exclusionary principle says that no two elements can have the same set of quantum numbers. No problem. So it looks like it's in the D block, and it is. And it looks like it's in period 6, but it's not, because D block, remember, is n-1. So it'd be 6 minus 1, which would be 5. So our n value is 5. Our principal quantum number is 5. It's in the D block, so the angular momentum number is 2. And we're starting the cycle over again. So we're going to go minus 2. And the last arrow is this guy right there. And it is pointing downward, so it's 1/2 negative. And that's it for this lesson on osmium. You guys be snarly, and we'll see you back here at Musin Chemistry.